Good afternoon. My name is Morgan Moe, and I am joined by my colleague Ram Santaboyina, and we will be presenting our project on the systematic testing and reliability evaluation of role-based authentication system using partition testing, finite state machine testing, and usage-based statistical testing. This project focuses on understanding how different formal testing techniques perform when applied to the same system and how they compare in practice. And in this project, we tested this system using 3 formal testing techniques. We then evaluated these techniques based on their ability to detect defects, their behavioral coverage, and the reliability insights they provide. The main goal was to understand how these techniques perform in a practical setting rather than just theoretically. The authentication systems are critical components because they control access to sensitive data and system functionality, and failures in these systems can lead to unauthorized access, user lockouts, or inconsistent behavior. And the key challenge in testing these systems is that their behavior depends not only on inputs, but also on system state and sequences of user actions. Traditional testing approaches often focus on isolated inputs and may miss issues that arise from these state-dependent or sequence-based interactions. And the main objective of this project is to compare the 3 testing methods in terms of their effectiveness, their effort to apply the required defect detection, and their ability to evaluate the system reliability. This visual essentially shows the system under test and includes functionality such as log in, log out, password reset, account lockout, and admin access. And a key characteristic of this system is that its behavior depends on both the input values and the current system state. So this means that even when correct credentials may not result in successful login if the account is locked or requires a password reset. This system in particular was selected because it combines input-driven logic, state transitions, and realistic usage patterns. These characteristics make it well suited for applying partition testing to validate input, FSM testing to evaluate state transitions, and usage-based statistical testing to simulate real-world behavior. And this allows for a meaningful comparison of all 3 techniques within a single system. The overall testing strategy involved applying these complementary techniques. So the partition testing focuses on validating input correctness. The finite state machine testing focuses on validating behavior between the behavioral transitions. And usage-based statistical testing focuses on simulating realistic usage patterns. And each technique captures a different category of defects, which makes them collectively valuable for comprehensive system evaluation. Partition testing was used to validate input correctness by dividing the input space into equivalence classes. We tested combinations of valid and invalid usernames, passwords, and account states. This approach ensured coverage of both normal and exceptional input conditions. The results of partition testing showed that the system correctly handles invalid inputs and enforces access restrictions based on account state. One important observation is that account state overrides input validation. For example, even when valid credentials are provided, a locked account still results in an access denial. This confirms that the system correctly prioritizes security constraints. And while partition testing is effective for validating individual inputs and boundary conditions, it does not fully capture sequence-dependent behavior or the interactions across multiple operations. So as a result, it's limited in its ability to reflect on how the system behaves in real-world scenarios.
Finite state machine testing was used to model the system's behavior over time. The system was represented using states such as logged out, logged in user, logged in admin, locked, and reset pending. FSM testing focuses on how the system transitions between these states based on user actions and system events. Under controlled conditions, all FSM transitions behaved as expected. Successful login and logout operations worked correctly. Repeated failed attempts resulted in account logout, and administrative access was properly enforced. These results confirm that the system's transition logic is implemented correctly. During the initial execution, several FSM test cases failed due to the system being in a reset pending state. This state prevented expected transitions from occurring, making certain behaviors unreachable. This demonstrates that FSM testing requires careful control of the initial system state in order to obtain valid results. Usage-based statistical testing (UBST) was applied under using a Markov model to simulate realistic user behavior. Instead of executing predefined sequences, this approach generates sequences probabilistically based on expected usage patterns. The results of UBST showed that the system behaves consistently under repeated execution. However, persistent states such as reset pending state significantly influence system behavior. For example, once a password reset is required, subsequent login attempts consistently result in the same outcome. Additionally, user states are isolated, meaning that one user states does not affect another user's behavior. An important insight from UPST is that real-world behavior does not always match ideal behavior. Higher failure rates were observed, but these were not caused by defects. Instead, they were the result of system states constraints. This demonstrates that UPST is useful for evaluating system reliability under realistic conditions rather than idealized scenarios. Now moving on to the comparison of the techniques. Each testing technique offers distinct strengths and limitations. Partition testing is effective for input validation but does not capture sequence-based behaviors. FSM testing is effective for validation logic and state transitions but require controlled initial conditions. UBST provides insights into realistic system behavior but can be more difficult to interpret. Uh, Moving into the discussion, the results from all three testing techniques together provide a comprehensive view of system's correctness and behavior. No major implementation defects were identified during testing. However, several important behavior observations were made. One key observation is the dominance of persistent system states, particularly the reset pending state. This state restricts expected transitions and limits how users can interact with the system. These behaviors are not implementation errors, but rather logical constraints that are built into the system design. Additionally, the system demonstrates consistent and deterministic behavior. For the same inputs and conditions, the system produces predictable outputs, which indicates that the underlying logic is stable and reliable. Another important observation is the system's reliability characteristics. The system behaves consistently across the repeated executions, producing stable outputs under similar conditions. There is no observable degradation in performance or correctness over time. Additionally, the system maintains proper isolation between users. Actions performed by one user do not affect the behavior of another user, which is essential for maintaining system security and integrity. These results indicate that the authentication logic is robust under deterministic testing and probabilistic testing conditions. Next slide, please. Key takeaways. The most important finding from this project is that the system state dominates behavior. Conditions such as account logout or password reset requirements can override input-based logic entirely. As a result, the effectiveness of a testing technique depends heavily on the system's initial state. Now, to summarize, partition testing ensures input correctness. FSM testing validates behavior logic. And usage-based statistical testing reveals system behavior under realistic conditions. When combined, these techniques provide a comprehensive evaluation of the system. In conclusion, the project applied three systematic testing techniques to evaluate both the correctness and reliability of a role-based authentication system. The critical takeaway is the significant impact of persistent states, particularly the reset pending state, which can dominate system behavior and restrict further interactions. Overall, the system demonstrates consistent, predictable, and stable behavior across different categories. And the combination of these testing techniques provide a comprehensive framework for evaluating software reliability.
So for future work, there are several directions that could further enhance this evaluation. One approach is to refine the operational profile using real-world usage data, which would further improve the accuracy of the UBST model. Additionally, exploring more edge cases could also help uncover behaviors that were not observed in the study. Incorporating usability metrics would also provide insight into how system design affects user experience, particularly in scenarios involving persistent states like password resets. And finally, evaluating system performance under load would allow us to understand how the authentication system behaves under more demanding conditions. And finally, this slide shows the references we utilize to gain further understanding of how to create our system and the most optimal way to show the comprehensiveness of each test applied to the system. And this officially concludes our presentation on the systematic testing and reliability evaluation of a role-based authentication system using partition testing, finite state machine testing, and usage-based statistical testing. On behalf of Ram and myself, thank you for your time and attention. If you have any questions, we would be happy to answer them. And you can reach out to us using the contact information on this slide. Thank you.